There you go. All right, usually it says the meeting is now being recorded, and I don't know why it didn't say that, but it says up there to pause the recording if I want, so it must be recording. Okay. Okay, it's showing recording on your screen. Good. I just submitted and got my license through UH, so that it'll go over 40 minutes, and we'll see how this goes. Whether we can keep the same Zoom ID, and that'll depend on since Michelle set it up. So I think we'll be able to keep it, but I don't know all the odds and ends of co-hosts and whatnot on Zoom. All right, now let's try the slideshow. Seems to be working fine. Okay. So we left off here talking about isotopes. And after we went over all those old classic physics experiments that determined the modern day structure of the atom, the nucleus, protons, neutrons, electrons. Okay, then we talked about isotopes, right? Same number of protons, different number of neutrons. Chlorine is this one they're using here, where AMU is atomic mass units, which is just the number of protons and neutrons. And there's two main ones, 35 and 37. We'll talk in greater detail. But what we're building about isotopes in nuclear chemistry, but what we're building up to here is why the atomic mass average that you see on the periodic table doesn't reflect a normal average that you've done maybe up until this point, or in general. Let me let in another person. And so you see that down here, this is straight off the periodic table. The 35.45 atomic mass units is obviously not the normal evenly weighted average, right? 35 and 37, you add those two together, divide by 2 would be 36, but that's not what we see. All right, so we'll get to that, back to that percentages in a minute. Just a refresher, right? Isotopes are the exact same element, same number of protons, so the exact same element, and thus they behave exactly the same, right? Same chemical reactions. Installed there. Right, but they have different masses. We saw that example on chlorine on the last slide. The reason for this is they have different number of neutrons. That gives the different mass. The way we talk about these isotopes, and again, you'll see this depending on who you take Chem 162 with, the usefulness of these different isotopes. But we identify them by the mass number because that's the thing that's different. All right, and this is what neon signs, why neon signs are called this. Again, atomic number is the number of protons. That's just the number you see on the periodic table. Then the mass number is the combination of those two. What we're building up here to, the important part here that's new, is the relative abundance, and that's how much is found on Earth. All right, so neon, for example, that makes up these neon signs. There's 3 of these, 20, 21, and 22, and they're about 90, and 0.3%, and then the rest 9 whatever. We'll come back to those percentages, and we'll do a couple, and there'll be one on the periodic or on your first exam. This one's walking us through this common way that we show these isotopes. So in Word, you can't put 2 numbers here. So they introduce it like this, and you need a special character to do this. They do this just here in this chapter. After this, you'll never see this again because chromium is the 24th element. So writing a 24 here for the proton number is slightly redundant. Then the mass number is the number by which these isotopes are talked about. So this chromium is called chromium 52. I know the number's in front, but that's how it's said, is chromium 52. You don't say 52 chromium. All right, the charge goes after it. So the mass number in front, the charge after it. Since there's no plus or minus written after it, which is what we'll do in a few slides, those numbers must be equal. And then we know it's the 24th element because that's where chromium is on the periodic table. The protons equal the electrons, so same number, and then the 52 is the mass, the total. We know that's 24 plus our mystery neutron number, so 28. Right, so pretty simple math, just as long as you know where the numbers are coming from and what to do with them. Predicting the stability is a Chem 162 thing. We haven't gotten there, so this information for checking isn't really all that helpful. Okay, elements undergo chemical reactions, and we'll get to those next slide. Sorry, I'm just moving. The chat box moved on me there. And the way they react has to do with the number of protons and the number of electrons that they have. The number of neutrons just is the mass number, but they still react the same. All right, so the number of protons determines the kind of element, and we'll see that they're very similar up and down the group or the column. Group is the chemistry way, column is, the more typical way. Rows and columns are how you look at a grid. Reactions, chemical reactions occur when you change the bonds, and the electrons are what make the bonds. So it's basically transferring electrons between elements is what a chemical reaction is. All right, so up till now, everything's been neutral, but what if the number of electrons doesn't equal the number of protons? That means that there's some difference in charge. So the only options are that it's neutral or that it has charge. If it has any charge, it's called an ion. If you have more electrons, it's called an anion. So that's negative, right? Because electrons are negatively charged. And then if you lose the electrons, there's more protons, and so it's positively charged, and that's called a cation. So these ions behave differently than the neutral atoms because the behavior of atoms is a function of how many electrons they have. Here, the example that they give us is in group 1, these electrons, these atoms have 1 electron, and as a neutral metal, they're quite reactive. But then as soon as they give up that electron and have just a positive charge, a +1, they're really stable. That's the salt in the ocean, right? Is essentially non-reactive. All right, so for some nonmetal to form an anion, it's got to gain an electron. And the location on the periodic table tells you how many electrons it wants to gain. All right, so fluorine, for example, 19 protons, 19 electrons. The fluorine now with an extra 1 is called fluoride. We'll get into the naming. The charge is written after it and superscript up above. So the number of protons doesn't change because it's still fluorine, but we've got an extra electron. The next example here they picked was phosphorus. So phosphorus went from neutral, then gained 3 electrons up to 18, so 3 minus. The way you tell the difference in the name of these is you put an IDE ending on the end. So fluorine becomes fluoride, oxygen becomes oxide. It's not a spelling competition. It's not an English class. And in most of our problems, it's going to be multiple choice. So it's not like you're going to have to, or you're going to lose points or credit on a test from spelling something wrong. Okay, so cations are almost always metals. There's a few other examples, hydrogen in particular, but basically it's all the metals. And what we have here is we've lost an electron. So sodium, we already saw where you lose that electron, so you've got more protons. That means you got to have a positive charge, and it goes with the column that it's in. So in the first column or group, it's a +1, and then in the second column or group, which is where calcium is, it loses 2 electrons, and it has a +2. The metals go first in the naming, and these names don't change. So the sodium neutral is a metal. The sodium +1 is still sodium, but it's just called the sodium ion. So nothing really to memorize or learn here, but not like the IDE ending for the anions is that hard to make note of. Okay, not a history class. You won't be tested on whose name goes with what concept or what experiment. We already saw that last time. Mendeleev is a Russian chemist, physicist, and he saw this repeating properties of elements, and basically he made up the periodic table. So what he did was start to arrange these elements. It's sort of like, I don't know if you've ever done this. I did this a long time ago with English classes where, you had to get your paper that you had to turn in a certain length. If you push the, fool with the margins of the font, you can stretch the paper out and make it a little bit longer. And he was basically setting the margins on his list of all these elements. And so when you set the margin, then the sentence starts over and you start a new row. And now these elements with similar properties, they start to line up. And then you could predict the properties of things that they hadn't found yet. So this is what the modern periodic table looks like. I'll put the one that I like on Laulima. You're free to use it. I'll email it out. It's not, mandatory or anything, but it's got a lot of color-coded stuff that helps more than this one. Just has lots of information that make it useful all semester long. Then this one is an introductory one where it shows you by color code when these things were discovered. And not too shocking, these orange ones here, a lot of these are artificially made in nuclear power plants. And you can tell here, again, a little bit of history, right? This is Einsteinium, Ferium, their name, Mendeleev, that's named after him. He wasn't alive then. They made these things at Berkeley, and so California, and then, Lawrence Livermore is where one of these labs is at. Anyway. So this is what Mendeleev did, is he had this list of all these elements, and then he noticed these properties are similar, so he set the margin there, and these things start to line up. So in his short little version, right, hydrogen kind of behaved similarly as these metals. We'll see that hydrogen and helium are really rare. They're really high up in the periodic table, and so they're kind of outliers. But helium was a gas, and so are the ones beneath it. And then these, as you set the margin there, these elements start to line up and have similar patterns. Let someone else in the room. So the famous example here is silicone and tin are quite a bit of ways away from each other. 28 versus 182. And atomic mass, now this varies on isotopes, so that's why the values vary. You can't predict. He couldn't possibly predict the number of neutrons in the different isotopes available on Earth, but he knew from setting those margins that there was an element in between these two, and it should have properties in between. Right, so this one was gray and white, and so the one the element that's in between these two rows of the periodic table should have some features in between it, right? In between the density 2.32 and 7.28, so something like this, 5, right? And then these, are what was measured. And this element is Ge is germanium. And we'll come back to these elements when we talk about moving up and down in the periodic table and silicone and computer chips and things like that. Okay, so where things are on the periodic table gives you insight about their reactivity and usefulness. This one is just doing metals, nonmetals, and metalloids. So hydrogen's right here, this blue square, and sometimes hydrogen could be put right here, right next to helium, because it's a nonmetal and it forms a gas and one of its bonding modes, which we'll get to at the end. And other times helium, which is right here, could be put right next to hydrogen over on this side. Now they're both not metals, so it kind of on this slide, hydrogen would be better over here next to helium. Anyway, so the blue ones are nonmetals, right? The tan or gray ones are metals, and these purplish ones are called metalloids. And this makes sense. If it's pointing out here, silicone, you've heard of the silicone chip that, this is what makes up computers and everything. You think about your phone, down here at the bottom is lead, and up here at the top is carbon, right? Carbon is what makes up diamonds or the lead in your pencil or a barbecue, what you cook with. That doesn't really sound like something that's going to make computer chips and be useful. And then if you've ever held a bullet or a gun, or some pipes and pans to cook with are lead, you don't want a cell phone that's super heavy, right? And if you're cooking on the stove with it, it conducts heat, right? You don't want your phone to get hot and melt. So these elements in here on this staircase, these metalloids, these are the things that are useful for electronics. They conduct electricity, but they don't conduct heat. They're not complete nonmetals that you need. You need them to conduct some electricity and do the things you want, but you don't want, also no one wants an extremely heavy cell phone, laptop, etc. If you've got an X-ray, they put a little lead blanket over you, and that's the other place you might have felt lead. So right here, it goes from 57 and 89 to 58 and 90. So really this portion here, the lanthanides and actinides, should be pushed in here, and then the table should be spread out. But that makes it too wide, and these elements don't get used much. So it just has this little offshoot out here that everyone knows belongs sandwiched in here. Okay, metals. So you've all touched metals. I don't think you've used keys to open a door, or ridden a bike, etc. Touched a change. Pennies are almost all copper. So these things conduct heat and electricity, right? You don't take your keys and stick them in a light socket. So we don't need to spend all of that much time on this. Malleable and ductile just means that you can make it into jewelry and wires and stuff. None of this is on a test. You already knew all this stuff. What's new and what we care about is that they can lose electrons and form cations. And for example, table salt or the salt that's in the ocean comes from sodium that's lost an electron. It's an ion. It's not a metal, solid metal atom that's in there. And when you looked on the periodic table, right, about 3/4 of the table is all these different types of metals. And they were all to the left and lower down. And so the nonmetals were over on the other side. And found in all three states, obviously, right? The best example of this is, it's not the individual element, but water is hydrogen and oxygen. And you've seen steam when you've cooked on the stove, and you've taken liquid water and put it in an ice cube tray and put it in the freezer and seen it solidify. Just like if you've ever cooked, conductors of heat and electricity, if you've ever made cookies before, you don't just take with your bare hand and pull the cookie sheet out of the oven. right? You go grab something that's a non-metal, like a towel, pot holder, etc. Some solids are brittle, think about toast, but some are buttery, right? And exist in all three states. Some are liquid, some are gases. But none of that information is new. What we care about now is that almost all of these gain electrons to become anions. And so salt that's in the ocean, or table salt, is sodium chloride, a sodium atom that's lost the electron, and a chlorine atom that has gained the electron. And again, I pointed out, except for hydrogen, which you could put over, and it depends on what features you're thinking about. They're all to the right in the upper side of the table. Right, and then the metalloids, those ones down the middle, and I already, pointed this out. These are the things you want that are going to make up semiconductors and electronics and whatnot. And it's because you want a mixture of metal and non-metal properties. It needs to conduct electricity, right? All your electronics, but you don't want them heavy like lead, or you don't want them getting hot. So different metalloids get used for different features to make all these electronics that we use. And that's all these green elements. All right, so similar elements then, by their physical properties, are in the same column. We call them groups or families. So if you're a chemistry major, then we definitely try to get you in the mindset of calling them groups or families. Groups is a little more common. I know that almost everybody is not, chemistry major, and might just be taking Chem 162 for the last Chem class of their life. So I'll interchangeably use the word column or group. It's not a big deal for us. Right, then the rows are called periods. Once again, periods is the proper term, but I'll occasionally say row, or I'll say periods, and especially in these Zoom classes, I don't have the camera up to see people's faces, but if I see confusion when I say period, I say that's reaffirm and say the period or the row, but they can be used interchangeably. I don't know our book too well in depth to have read through it to see how often after they introduce it do they just use period. Okay, so main group is groups 2 and then 3 to 8, and depending on what periodic table you have, what book you have, which periodic table you want to use, they use this A and B numbering system. And so the B are the transition elements. They're all metals, so a lot of times called transition metals. They're obviously elements, so sometimes that phrase gets used interchangeably. And then the rare earth ones, but let's just pull this up. So here's the transition metal ones, all the blue. And then the main group here, they get labeled like 1, 2, skipped over, then 3, 4, 5, 6, 7, 8. Other books or other periodic tables will call 1 and 2 are still the same, but then they'll call this 3 and go all the way over and call till they get here to where helium, the noble gases, and call that 18. I think the periodic table that I give you guys, it has both numbering schemes, so you can pick whichever one you like better. When you're taking the test, you'll have the periodic table handy, so it's not like you need to memorize these things anyway. All right, the individual families, groups, columns have names. So the alkali metals are here. The first ones, that's group 1. The alkali earth are group 2, or transition metals are in the middle. The noble gases are on the far right. Halogens, second over. So again, depending on the numbering system, 8 or 18, 7 or 17. And then those lanthanides and actinides are down here, but we won't really use those too much. And again, they're inserted into the table. And just like the way the main group here, you would go 1, 2 and skip over. this lanthanides and actinides could be pushed in there, and you can make the table much wider. But these lanthanides and actinides don't get used too much in the real world, so the periodic table commonly looks like this. Okay, hydrogen is this rare, unique element on the periodic table. It's super high up there. It's the first element, and it has a few things that make it behave like a group 1, but it also has a few things that make it behave like a halogen or a group 7. So it's colorless. Diatomic means it forms one bond with itself and exists as H2. Then it's a really low melting and dense metal. This stuff, we haven't covered how chemicals react yet, so there's no way you should know any of this, or you won't be held accountable for how it behaves. And especially this hydride thing, you wouldn't use that off until OChem. And we haven't even introduced acids. That's for Chem 162 as well. So you won't be held, accountable for memorizing all this stuff. It's just introducing it. Again, chemistry is like a series of Venn diagrams, and we're covering the periodic table now because it's like a roadmap through the world of chemistry. And so it's introducing things that you'll see in future chapters throughout the whole book. Okay, then everything else in group 1 besides hydrogen, they behave pretty similarly. Right, so hydrogen is placed here, but it doesn't really go here because it's not a metal. These ones tend to be softer, and that literally means to the touch. They're real reactive as metals, so it's rare to actually touch them unless you're in a chemistry lab. Low melting points and low densities. The flame test won't make sense till we get to like chapter 7. They're really reactive, so you don't find them in nature. If you've ever watched an old Western or know your history about, say, San Francisco, the gold rush in 1849. If you're panning for gold, you actually find gold nuggets, like a chunk of metal, but that's not the way these ones are. These are so reactive that you never find them. Like this chunk here that they're showing you of sodium, that was made at a chemical plant or a laboratory. We find it as the ion, like in the ocean. And then once they lose that electron, then they're stable in water, and that's what seawater is. Again, the reactivity, we haven't even got there yet. Beryllium, you move on down, you move one over. It's alkali earth metals instead of alkali. Group 2, it wants to lose 2 of the electrons. The flame test we won't get to for a while. And in some of the labs I know at the different junior colleges and at UH, they do this flame testing. You actually do it. I don't know about for you guys at HCC. These ones are still reactive, but not as reactive as the group 1. And again, what oxides they form, we haven't got there yet, or their basic character. We haven't even talked about chemical reactions. So this is all just foreshadowing for things that you'll revisit in future chapters and Chem 162. All right, skipping over across the periodic table, and this is where hydrogen could be above fluorine. And the reason for that is they're nonmetals, and they all form a diatomic, which di means 2, atomic means atom, and F2Cl2, etc. Right? They form this X2 diatomic species. And what you see here is on the edges of the periodic table, things are fairly reactive, right? The group 1s were reactive. Group 7 here, these things are reactive as well. Then here again, future foreshadowing here, what they're reactive with. We haven't even talked about chemical reactions. So we'll get, and then the trend of how and why they react as acids. In Chem 162, you'll do the math behind that. Then helium and the noble gases are completely non-reactive, right? So if you've ever been at a kid's birthday party, you grab the balloon, undo the knot, and breathe it in, you don't choke to death and die. It doesn't react with your lungs. You breathe it out and your voice sounds funny. They're all gases. So if they're gases, obviously they have low melting points and boiling points. They're basically unreactive. It's extremely hard to make these things do anything. There's not a lot of these other elements, krypton, neon. The way that you obtain these is by pumping down normal air and then separating these things out. And helium is what we use in blimps, right? In balloons like this. And there's a shortage of this nowadays, which is a long story why, but so helium balloons, I don't know if anybody out there has actually had a birthday party where they needed to go buy them. The price of helium has been skyrocketing in the last 4, 5, 6 years. And the reason they're unreactive is it's hard to either give it an electron or remove electron from it. So the reactivity we're starting to hint at here is a function of if it wants to gain or lose electrons. All right, so the ion charges basically comes from the position on the periodic table. Metals almost always give up their ions, and for us, they always do. I'm not going to put any weird exceptions on. And non-metals, the same thing. So metals positive, non-metals negative. And in general, the charge equals the group that it's in. A few exceptions, but we're going to be more typically trying to stick to the trends and not look at rare exceptions of things. So group 1 plus 1, group 2 plus 2. The transition metals have some variety to them, and that's really for higher chemistry classes. We won't worry about it. All right, then group 3 plus 3, and aluminum is the most common one. Boron's a special case for too long of a story. Notice how carbon here is left out because it's right in the middle, right? Notice this trend of plus 1, 2, 3, and then nothing's mentioned, and then minus 3, minus 2, minus 1. And so 4 is right in the middle. So does it want to gain 4 electrons or lose 4 electrons? Well, that's the whole world of organic chemistry, is it can do both because it's right in the middle. So it's a very diverse element, and that's why if you just look on the courses in college, you can spend a whole year just studying basically the one element and all the things that it can do. Okay, so now we know a little bit more about the elements. Let's get back to that number. So on the periodic table, the chlorine was the one we looked at, right? It was, the mass was 35 and 37. So the normal average that you're used to, it should have been 36, but it's not. On the periodic table, it's 35.45. So why is that? It's because it depends on how much of each isotope you have. This little symbol here is called a summation, if you haven't seen that in a math class before. So the atomic mass that we observe here on Earth is a function of adding together the isotope's abundance times its mass and adding that to every other. So the summation means you do this property for every example, so every isotope. All right, a mass spec, which if you're a science major, you'll use this at one point. This is how they determine a lot of crime scene investigation. You know, if you want to make sure that a bullet came from some, batch of bullets and match a bullet from one to the other, that type of thing. A mass spectrometer is something that does this. So it busts up the molecules and they fly in fragments, and then you can determine the structure by the mass. And it's the reason it's introduced here is because we're talking about isotopes, and it's similar to that cathode ray experiment. We're talking about it here because when you have chlorine in something, you see this difference in mass of 2 units that's attached to it. So you have, carbon and hydrogen, oxygen are basically all one isotope, like 99%. If there's a chlorine on that molecule, then you'll see this type of spectrum that has this, they call it a staircase, right? Because one's bigger than the other. And the chlorine's, roughly, 70-30, something like that. And you see this in mass spec, so you could possibly see this in the future. This is, not an exam or anything. This is what a mass spec looks like. you get your sample into the gas phase somehow, and then you have it flowing. Usually it's gas that's pushing along, but there are other ways. There's different ways to get things ionized, and then you accelerate them a couple different ways. This is doing it by charge. Then you have a magnet, and then something that detects it. And so heavier or lighter move after the magnetic field, and the detector can then figure out from that distance once you calibrate it. So you have to put in something and calibrate it, and then it can tell you about unknown things. Okay, so the problem, there'll be one of these on your first exam, and it's going to be a made-up number, because otherwise you would just go to the periodic table and circle the value, right? But this is explaining why we see the number that we see on the periodic table. So what it's saying is you have copper 63, that it's about 79% is its natural abundance, and then this is its highly technical exact atomic mass units, but basically 63. And then it only has one other isotope, and that's copper 65. Again, here's its hypersensitive. It's not truly 65, it's 64.9278. Anyway, the point of this one is that we've got these two isotopes. The percentage has to equal 100, so about 70% is 63. The rest of that, about 30%, is isotope 65. So what is the mass? Well, it's what's called a weighted average. It's not the normal average, right? So we want to multiply the fraction, that percentage, times the mass, and then add those values up, right? So about 69% and about 31% of the 63 and the 65 isotope. And so we should get a mass that's much closer to the higher percentage isotope, right? If it was 50% of each, that's a normal average. This is a weighted average. So this answer of 63.5 makes sense. It's closer to the 63 isotope than the 65, and it should be. Okay, all these things we've been talking about, atoms, elements and atoms, are really, really tiny. So we've got to group them together. This is called Avogadro's number, named after the scientist that discovered it. And just like there's a dozen donuts, that's 12. If you go by a ream of paper is 500 sheets of paper. A mole is just this strange word they picked, but I don't even know who picked it, probably Avogadro, but a mole means a grouping of 6.022 times 10 to the 23rd. So the atoms are so tiny that you have to group this insanely huge number of them together to do anything with them. And this was picked and agreed upon by everyone as a mole. Where this came from is, imagine you're a scientist and you're playing around and experimenting and trying to figure these things out. The way to do that is to use the elements that are there. And after a campfire where there's just ash, that's basically pure carbon. So they could do things with carbon. And that's how they got to those, we covered this a little bit earlier, the mass of a proton and a neutron. So carbon-12 was exactly those, 6 protons, 6 neutrons, so 12 mass units. And if you group the 6.022 times 10 to the 23rd atoms together, then it turned out to weigh exactly 12 grams. And since everything's based on protons and neutrons, then this applies to 1 mole of any element. And carbon is almost exclusively carbon-12. Okay, so we'll use this number. There'll be 1 or 2 problems, at least one on the first exam where you'll use this, and you'll see a sample problem coming up. Then likewise on the final, you'll see 1 more of these problems. But after this, we won't go back and forth from individual elements to moles. We'll just use moles, and we won't use this number again. So here's a good example of this. Calculate the number of atoms in 2.75 moles. So this is just a dimensional analysis conversion, right? We want to go from moles to atoms. We know we have this relationship, just like there's 24 hours in a day. You need to set it up correctly. You're in moles, so you want moles on the bottom. The moles are going to cancel, and we get into atoms, and that's the units that it asks us for. So this one's pretty simple, right? We're just one conversion factor, and obviously it's with Avogadro's number that we just introduced. Okay, so what we'll use for the rest of the year and in Chem 162 is what's called the molar mass, which is the mass of whatever grouping of elements in grams that is a grouping of 1 mole of them, right? So if you group a mole of them together, what is that mass? And it's just the number you see on the periodic table in grams. Instead of using AMUs, we have to use enough material to weigh things out on a scale, because these atoms are so tiny. So the number you see on the periodic table, hydrogen, for example, is 1.008, carbon's 12.01, and that's because it's carbon 12, but there's 1% that's carbon 13, so it's slightly above 12. Well, if you group a mole of these together, then that AMU becomes a gram amount, and this is what you'll use in lab, right? We have scales that weigh out grams, a decent size for us to work with, not the individual atoms. And so here all they're showing you is what these things look like. All right, so one more example. Calculate the moles of carbon in 2.065 grams of pencil lead. So again, more dimensional analysis. We're in grams. That's not what we want to be in. We know a couple different relationships. We know how many grams are in a mole from the periodic table. And so we need to set it up right where the unit that gave us grams is on the bottom. Those two cancel each other, and now we're in the unit that we wanted, that they requested, moles. And notice the E gets left off. So you can put the E, it's kind of a British thing there. They pronounce words and put an extra E on some words, but either one is fine. And the American way is a little bit more, is a bit more common to just put MOL. All right, so this one's going to combine the two, right? From atoms to grams, and moles is what gets us in between there. So we combine the last two problems, right? From the periodic table, you know how many grams are in a mole, so we set that one up first. Grams on the bottom, so it cancels. Now we get out of moles by Avogadro's number, right? So from grams to moles, from moles to atoms. And the number should be really large because the atoms are tiny. Okay, we made a pretty good pace there. That was chapter 2. I want to just, while we're here, let me find. I'll show you the periodic table that I'll put on Lalima and be sending out. It's opening slowly. Okay, and all I did, this is not anything amazing. All I did was Google image search periodic table, found the one that I liked, 10 years ago or something, and then slapped it into a Word doc and made a PDF out of it. I'll post this on Lima and email it out to everybody as well. This is a really handy one to have up during a test. So I know it looks a touch confusing at the moment because there's lots of numbers and all kinds of things. And we individually covered one topic, one issue at a time. But the color version of this one is really handy. So for example, in here in this box, where the letters are written are blue. So up here, right, that hydrogen, it's subtle, but right, that's blue versus black writing. So it's a gas. Over here, you can see this trend in the noble gases, right? So fluorine and chlorine are both written in blue because they're gases at room temperature and pressure. And then now bromine is a liquid, right? And then iodine here and astatine are both in black because they're solids. The rest of these are all in black because they're all metals with the exception of mercury. The metalloids are the red ones, right? The blue and slight variation, right? The purple, these are all the metals. And right here, you could see why this hydrogen, it's a non-metal, could be right here above fluorine, also because of the bond that it forms, that H2. Anyway, this is a handy periodic table. The atomic numbers there, then the mass number, this little, both of these, this little chart reminding you what everything is. The groups, there's the numbering. So whether you want to do 1, 2, and then here's the A-B system, right? So 1A, 2A, and then 3A, 4A, 5, 6, 7. Or if you like the 1, 2, 3, all the way across to 18, it presents it as both. Okay, so chapter 1 was sort of just basic science, right? And then chapter 2 was really just introducing the periodic table. It isn't really here until chapter 3. I know this is kind of fast, but there's not a terrible amount of math or anything we did in chapters 1 or 2, the temperature scale and then protons and neutrons and then the mole. Is kind of it. And with the atomic mass, the weighted mass. A lot of the stuff we'll do the rest of the semester, and Chem 162 is based on the foundation and the learning of chapters 3 and 4, where we really talk about the chemicals, putting them together, and then chapter 4, how they react with one another. All right. There. Sorry. Okay, so usually the way these chapters work is the first slide or two shows you something that you have seen or some exposure to, and tries to make it interesting to you. So the way this one's starting out here is it's introducing hydrogen and oxygen, right? So oxygen is the gas we breathe, so supports combustion, right? If you've ever had to put out a fire, you can smother it. Obviously, you pour water on ice, that gets rid of the temperature that comes from a fire, but if you want to stop it, you can just put a towel over it as well. Hydrogen you wouldn't have much exposure to, but if you've ever seen the Hindenburg is this blimp that the Nazis used in the 30s and it caught fire. So hydrogen is also a hot topic in fuel cells. And it's got a lot of energy in it, but it's a flammable gas, so it is explosive and somewhat dangerous. You have to handle it appropriately. If you're a scuba diver, there's something called HELOX where they mix these two. But notice, all right, that's hydrogen, oxygen, right? Supports combustion, explosive. Now sorry about the Hindenburg, the blimps that the Nazis used. Blimps use helium nowadays because hydrogen is flammable, so it's much safer. But hydrogen or helium is getting expensive these days. All right, so it depends on the connectivity and how you combine these elements and put them together. Water, you probably know the formula of it is H2O. So there's two hydrogens, that's the white elements. Oxygen's always red. This color coding stays the same whether you're in higher chemistry classes or in bio classes. And it's not a gas, right? Hydrogen and oxygen were both gases on their own, but combined together to make water. It's a liquid with a pretty high boiling point, right? And this actually is the product of combustion. And you can use it to put out a fire, right? If you've ever been camping or cooking or whatever, barbecue, and you're done with it, especially at the beach or something, you don't want someone to fall into it, step on it, anything, something like that. You can just pour water or especially throw ice on it that negates the heat. And the reason it puts the fire out, extinguishes it, is water is most of the time the product of combustion with anything that has hydrogen in it. And so when you add the products, more of the product of something onto it, it stops the reaction, which is a bit further beyond what we've gotten to. So on the left, if you put these two in a balloon, this is on the atomic level, what you would see is these two diatomic molecules, oxygen and hydrogen, bouncing around inside the balloon. But once you combine them, you get H2O water, where you have these little water molecules bouncing around, and now it's a liquid, and a fairly high boiling liquid at that. When you have cuts or scrapes, you can clean them with hydrogen peroxide. And the chemical structure is like it sounds, right? Per means one of something, one per another thing. So like miles per hour. This is hydrogen per oxygen. So one hydrogen for one oxygen. So we have two hydrogens, we must have two oxygens. And right, hydrogen can be used as a flammable gas, H2, and then the product of that is water. And so hydrogen peroxide is a molecule that's directly in between those two. And basically what this does is it can half combust something, if that's the way you want to think of it. So before things like hydrogen peroxide, during the Civil War and before that, if you had a wound, they didn't want it to get infected. One of the ways to make sure it doesn't get infected is just to burn the wound, which is obviously extremely painful. But they would just take a hot iron and burn the wound, and that would kill anything that would cause the infection. Obviously extremely painful. And we don't do that obviously nowadays, but hydrogen peroxide still hurts when you put it in a cut. And it's because what it's doing is it's donating this oxygen atom. And you get water, hydrogen peroxide, but that oxygen atom goes in there and starts breaking bonds and making new ones and destroying whatever's chemically in there on the chemical level. All right, so the way atoms come together is a function of where those electrons are. And we've got two different types of bonds, ionic bonds, and that's where the electrons are transferred completely. And we kind of saw that with sodium chloride, right? Or covalent bonds, and that's where they share the electrons. So this picture right here, imagine this is basically hydrogen. It only looks like one electron, but there would be the one proton from each hydrogen, and then the electrons would be in between. So opposites attract charge-wise, and we've got a plus, minus, plus, and that's what holds that these diatomic molecules like hydrogen and oxygen together. So just like the hydrogen and the oxygen combine to make water, another example, right? Sodium, the metal, again, you don't find this in nature. This was made in a chemical plant. Is when it's neutral, but you give up that, lose that electron, and chlorine on its own is a yellowish gas. So if you give up an electron from sodium and give it to a chlorine atom, you then get the sodium ion and the chloride ion. And this is that salt, right, on the atomic level. And then, I don't know, this picture is pretty zoomed in. But if you've ever gotten out of the water, the ocean, and you weren't somewhere where there was a shower, you'll see this, the little crystal salts on your like your arm hair or something, or on your skin. Almost looks like a dusting. And if you look on it on a microscope, you can see it has this real crystalline nature. Okay, the baby beginnings of OChem. So there's different ways to show these chemical formulas, and each one of them gives you information. And obviously, as you see here, as you move along, some of them give you more and more information. So, right, just the molecular form is just the elements, and then the subscript after it tells you how many of those elements are there. So 1 carbon, 4 hydrogens. If you draw it like this, structurally, this tells you which elements are connected to which. And CH4 is methane or natural gas. So if you have a gas stove, or then maybe you've seen it or used it. And these further ones won't really matter for us or for you until you get to organic chemistry or some bio classes. The ball and stick here tells you more about the shape, right? This is really looking more like a tripod, whereas over here, this one looks like an X or T flat on the page. And then these space filling ones, again, start to tell you more about how it looks, how a molecule is in 3 dimensions. The empirical formula is the simplest formula, the ratio of the elements to one another. So, for example, table salt is sodium chloride. It's in a 1-to-1. Doesn't describe how many are there. Let's say it was 2-to-4, right? It describes the simplest in 2-to-1. It doesn't tell you about how they're attached or their shape. It's simply just telling you the lowest common denominator when you've added fractions together. The molecular formula is the actual molecule, however it exists, the number of atoms attached to it. So again, sugars are like this, where sugars are carbohydrates, a carbon, and then a hydrate, a water, so CH2O. But there's all different types of sugars. You've heard of fructose and glucose and galactose. Anything with an ose on the end is a sugar. So that they all have that same carbon, 2 hydrogens, and an oxygen, but they can have 7, 6 carbons, 5, 4, etc., 12, etc. The structural formula, and we won't get to this till the end, but it gives you that 3-dimensional shape. And the lines are bonds, and it's 2 electrons per bond. So kind of like cheeseburgers. If you got a double burger, then there's twice as many. So if there's 2 electrons in a bond, a double burger is going to have twice as many. So 2 times 2 is 4, right? Then your triple burger has another burger, so 2 times 3 is 6. We won't do the ball and stick till later. The space filling is really more of a bio thing. So, but the models give you the 3-dimensional shape, and we'll do that at the end of the semester and see that it is pretty important. But for now, we're going to focus more on these chemical formulas. Hydrogen peroxide is a good intro to this, right? The molecular formula is really that there's 2 hydrogens and 2 oxygens. The empirical formula, again, lowest common denominator, you just divide by 2. Right, so its empirical formula is HO, but how it really exists is H2O2. Just a couple of these other ones. You don't have to have these memorized. This is organic chemistry stuff. Benzene looks like this, and it's an additive in gasoline, and this ring type structure has lots of usefulness. But the point of it here is that it exists as C6H6, but if you divide both of those by 6, its empirical formula is CH. And then here's one of these sugars, right? The space filling model starts to get confusing as you've got lots of elements, right? But we call them carbohydrates. So there's that carbon and then a water, a hydrate. And so all these different sugars, all you're doing is multiplying this. I think like lactose is 4 and fructose is 5, glucose is 6. I don't remember all my sugars. Right, then this table just summarizes these things. And for those that are bio majors, this is the common way you draw out sugars. And it gives a few examples here of all these, ball and stick and formula, etc. Okay, one of the drawbacks whenever I put it in that slide view is there's no clock, so I almost lost track of the time. We're a touch over there, so we'll stop here and we'll pick up. These holidays are weird. It's been a week. We'll pick up here on Monday. Again, wait, is it? We started at 12:30. Oh, I'm sorry. We can go all the way to 1:45. Just kidding. All right, so we'll go a little further then, obviously. Yeah, the way glucose is shown here. If we'll have these modeling kits, and if you're a bio major, I strongly suggest you buy one of these modeling kits. They're really handy for us, but if you're a bio major, you're going to see all these things again. Okay, so here again is a snippet of the periodic table, and why this hydrogen is a lot of times put above fluorine is it takes on H2, right? And oxygen and nitrogen, we'll get back to those, but it could be right here above where it goes H2F2 chlorine, Cl2 Br2 I2. So these ones are good to just memorize, or a good thing to do, I'll email out that periodic table, is print that out, and during class or when you're studying, make little notes on it that are handy. So for example, like this, next to hydrogen, you write an H2, the whole group 7A, right, X2, and nitrogen and oxygen, because this is how they exist, right? They come as two atoms attached. These other ones aren't necessarily important. They're true, but unless you're a chem major, we're not going to use these phosphorus, sulfur, and selenium ones that often. So here you can see why this, hydrogen could be put over here right next to helium above fluorine. Is they all come the same and they form one bond, and so they make a diatomic. So just a couple of examples, all right? This pro-PRO is for things that have 3 carbons. Baby OChem, not worth it. You don't need to memorize it, but all propane is C3H8. Then here's our table salt again. Those ionic compounds, these are kind of the simplest. That's why they're going to cover them first. And then our last chapters are on the covalent. We'll revisit those and talk about their bonding. And then OChem is basically, a whole year of non-bonding carbon interactions. It's a metal and a non-metal. The metal is always written first, non-metal second, and then it forms this 3D array of these different anions. The polyatomic ions, we'll get to them yet, and they are like they sound. Poly means many, atomic means atoms, and so they're this many atom ion. So our metals and nonmetals make up these ionic compounds. The total charge has to be 0. So what this means is that the charges have to balance one another. So for example, sodium is in group 1, sulfur is in group 2. So a +1 and a -2. The charges don't equal, so we need twice as many sodiums for every sulfur. So our formula should be Na2S. Right, pretty simple math. You just need to know from your periodic table what element has what charge. One of the simple ways to do this is this crisscross method, right? So you go and you grab the symbol, you know what the charge is of your metal, of your non-metal, then that becomes the subscript of the other. And then you need these to be in the smallest whole digit number. So when you had to add fractions together, you know, adding 1/3 plus 1/4 or 1/2. And then you can double check that the charges cancel each other. So let's do an example here. Let's say it's aluminum. You go to the periodic table, it's in group 3, so it's a +3. Let's say the other one is oxygen, so it's in group 6, a -2. We write the metal first, the non-metal second. Crisscross those charges, those become the subscripts, Al2O3. Does that make sense? Aluminum, if we have 2 of them and it's a +3, that's a +6. Oxygen, we have 3 of them and it's a -2. +6 cancels, -6, and so we're correct. Now, these are a little bit difficult to put on a test because they're kind of too easy to look up. So you'd probably be given a made-up one, an element that's not on the periodic table, and I tell you the charge, something like that. Here's just a couple of examples. So potassium is in group 1 +1, nitrogen is in 5, so -3. So we need 3 sodiums. And these all come in pretty simple 1 to 3, 1 to 2, 1 to 1, 2 to 3, right? Calcium +2, bromide -1, so we need 2 of them, 2 to 1. Aluminum, and then now not with oxygen like the last example, but with sulfur. But the charge is the same. So the same aluminum has 2, the thing with -2 has 3, 2 times 3 is 6. Right, so pretty easy math, just as long as you know where the numbers are coming from. All right, so to go from the formula to the name, the metal always goes first, the non-metal second. Here's a first look at polyatomic ions, and we'll get to those, and I'll send you out a sheet. If it was an in-person class, I'd say memorize them, but you can just have the little cheat sheet taped up on the wall, and I wouldn't know anyway. So, but they have some common names like baking soda. All right, so the metal name, you don't change it. The metal name stays the same. Variable charge means one of those transition metals, right? And then you indicate the charge by the Roman numeral after it. If it's a polyatomic ion and there's only one for us, you just write that. The anion is where it changes, is where you have that root of the name, stem or root, same thing, and then an IDE on the end. So again, from the periodic table, just the group tells you the charge. The name doesn't change, not too much to spend a lot of time on there. The transition metals have some variable charge, and this is, iron. This is one of the ways that your blood is red from iron, and it binds with oxygen. That's how we breathe. And its ability, a lot of these metals, their ability to fluctuate between charges is what makes them do really cool and important stuff. The naming over here, it's not a spelling contest, and I'm not going to test you on having memorized which one's ferrous and which one's ferric. And again, especially you could just have this slide printed out and taped up on the wall, and I wouldn't know. So the point of this class is to understand the math that's going on and build up the structure and understanding, not to test people like it's a vocabulary or a spelling contest. Okay, then carbon, you rarely see it as this carbide, again, because it's group 4, could go +4 or -4. So we'll revisit that, and you won't see that in many examples. I certainly won't test you on it. The rest of these, you just cut off the end and put the IDE on the end. So nitrogen becomes nitride, oxygen becomes oxide, fluorine becomes fluoride, etc. All right, so metal ion first, non-metal second, metal name, IDE ending. Let's do a couple. CS is cesium. It's in group 1, a +1. Fluorine is fluoride, group 7. Name stays the same, IDE on the ending, cesium fluoride. Right, pretty straightforward. Again, this is a tough thing to sort of test you on in an open book, open note, online type of test. So this is just for explaining and giving a few examples so that the rest of everything we do all semester makes sense. The first one, potassium, and then change that ending for the non-metal chloride. The next one, magnesium, group 2, bromine, group 7, so -1. We need 2 of them, magnesium bromide. The last one we already did and saw before, aluminum sulfide. None of these charges are variable. So then what about if it is a transition metal? Everything's the same, it's just you have to indicate the charge. And you do this by putting a Roman numeral in parentheses. Otherwise, it's the exact same thing. So AU is gold. S is in group 6. Its charge can't change. Right, so since the sulfur can't change and it's a -2, and we've got 3 of them, that's a total of -6. Then if we have 2 gold atoms, they must be +3, right? +3 equals times 2 is +6. -6 plus -6 neutralizes +6. So we know what the charge is on the gold in the roundabout way because the charge wasn't variable on the anion. Copper can be +1 or +2. In this example, we've got fluoride that it's bonded with, and that has to be a -1. So if it's in a 2-to-1 ratio, then the copper must be copper 2. So copper 2 fluoride. And the point of this, again, is just so that, again, hard thing to test you on in an open book, open note test. But it's just so that you get the correlation between the formula you see here and the name. And it's really important for in lab, if you were in lab going to grab a chemical, you need to grab the right chemical. And going from the chemical to the name and vice versa. So a couple other little more challenging ones, right? Chlorine's -1, and we've got 4 of them, so that must be titanium 4. The bromine is a -1, 2 of them, so Pb is lead, must be lead 2. Here's that typical 2-to-3 ratio. Sulfide, sulfur is -2, and there's 3 of them, -6. If we've got 2 irons, they must each be +3. And this one just walks you through the same thing, doing the subscripts. Right? Manganese and sulfide, 4-to-2. But you can really divide that by 2 and make it simpler. Okay. It's been a while since I've done an hour and 15-minute class, but I got the time right here. 1:45, right? We're 12:30 to 1:45. Not meeting for a week almost made me forget. So we'll pick up here on Monday. We hit stop. I hit the unmute. So if you want to hang around and ask questions, I'll put that periodic table on our Laulima under the resources tab, and I'll also email it out to the class. Feel free to hang around if you want to chat about anything. Otherwise, I'll see you next week.
Yeah, I have a question about Baking soda. So what's the naming convention behind the ion bicarbonate? Because like carbonate is just CO3, but you introduce a hydrogen and it becomes bicarbonate.
Yeah,
Doesn't really make sense to me. Because isn't bi too?
yeah.
Stands for
Hold on. Not sure if it's so a lot of these names, if I go, here's some of those, like there's the carbonate and uh this bi thing becomes like bi is two, but it's also bi means like split between both. So the sulfate is sort of split where you can have this attached to a hydrogen to counteract the -1, but the hydrogen's already there. So it's a sodium, hydrogen, and then the sulfate. And once things get named, it's really difficult to undo the names.
okay, yeah, no, that makes sense. And then I guess my other quick question would be so elements in the same group, they react similarly, right?
Yeah.
And so why, I mean, maybe they do, I'm just not aware of it, but why is carbon like so unique? Because lead is in the same group, but I don't hear about like hydroleads. You hear about hydrocarbons, like big long chains. But why doesn't lead form like giant chains? Or does it?
Let me go. I'm getting there. The reason it doesn't is because as you move down, you cross that staircase of metalloids. So at the top, carbon is not a metal, right? And you know, it's lead in your pencil and a barbecue, charcoal, and then the elements that are in between. So these are the ones that all make up all the electronics: germanium, silicon,
Okay.
tin, right? And it's because they have features that are in between, right? Like silicone you can make oils out of, kind of similar to plastics and polymers that are similar to carbon-based ones. Then as you move down, they get heavier. And you're right, lead is a standard traditional metal. And so it's because you cross those staircase. So these are all these elements that get used in electronics. And aluminum, it depends on who you ask. Traditionally, it's painted in blue here, but right, little dinghies on boats, or you know, you put a little motor on it, you can go fishing in it. They make boats that float out of aluminum. They don't make them out of lead, right? So
Yeah.
as you move down, the features change, but it happens to be in group 5, 6, and 7 here. You go from, especially 6 and 7, you go from something that's a non-metal, and nitrogen's actually a gas. Then as you cross over, you get down to classic metals that you think of, like car keys and the frame of a car and things like that.
All right. Yeah. Thank you. That was helpful.
Yeah, okay, cool.
Have a good rest of your day.
You too.
I have, hello.
Yeah,
So I have a, when you did the add addition for like water and then you, what's it called? You rounded it down or like you simplified it? Uh,
I'm not sure what you
it,
mean.
uh, yeah, I was struggling to actually form this question.
The chemical, so like hydrogen peroxide, where was that?
H2O. Yeah, that one. Oh, wait,
Hydrogen peroxide or water?
water.
Oh, that the first one where so hydrogen, the element versus water, hydrogen and oxygen, the separate elements versus water that's made of hydrogen and oxygen, H2O.
All right, yeah, I definitely got lost trying to ask this question. And why is it that neutrons are actually needed if the protons are much larger in mass and they still cancel each other out with the electrons? What
So
wouldn't
the protons are in the nucleus and they're positively charged, and as they build up to larger and larger elements. You build up too much positive charge. The neutrons are basically in there to buffer that positive charge and keep the element happy in this nuclear view of it.
Okay, so it, okay, so even if the charges cancel out, it still needs the buffer?
Yeah, are we talking about the atomic view of the nucleus, or you mean
Yes, like atomic view.
okay. So that was really more like last chapter 2 than chapter 3. Right, so here, like
Alright,
carbon, for example, it has 2 protons, but like charges repel one another, and so even though these neutrons aren't negatively charged, the neutrons are in there to buffer and put space between the protons. But it's all
okay,
just a feature of the way they behave, even if, you know, the description of why doesn't terribly make a lot of sense. And if I go to the periodic table, so, right, it's basically in a 1-to-1 ratio. So helium, for example, there's 2 protons, but the mass is 4, so that means 2 neutrons. And then carbon is 6 and 6, so 6 to 12, 7 and 7, 14. And it's in this kind of 1-to-1 ratio, right? 10, and then the mass is close to 20. But as you get down here, pick this one, rhodium, for example, 45 and 45 is 90, but the mass is closer to 103. So as you get more and more protons, you need more and more neutrons for the atom to be happy.
okay,
And for our class, it just is the way it is. Like, you know, you're asking something that really a nuclear physicist would love to just ramble on and explain, but it's kind of beyond the scope of our class.
okay. Oh, I think I have a better way to rephrase the water question.
Okay.
So water's H2O, and I know O2 is oxygen, and you need 2 hydrogen to go with it, right? So if you add it, if I remember right, it's like 2H2O, but why is it not called 2H2O rather than H2O?
Sure. I'm pulling something up here. Okay, so hydrogen is a gas and its formula is H2. Oxygen is O2, and you're right, water is H2O. Those formulas can't change. If you don't have, if your formula was H2 and then O2, that's hydrogen peroxide, it's not water. So if you can't change the formulas of chemicals, otherwise they're no longer that chemical. So when you burn hydrogen and oxygen in what you've heard about fuel cells, you actually need twice as much hydrogen to oxygen.
Okay, so when you read it, like that formula right there, so does that mean you need 2 of H2 to mix it with 1 O2, but 1 oxygen?
Yeah, and then you get 2 water molecules out, right? The atoms have to add up, right?
Wait,
Because oxygen doesn't come as a single atom, it comes as O2. So you multiply the number in front by the subscript behind, right? And there's an understood 1 right here, right? Obviously,
yes.
there must be 1 there. So 1 times 2 is 2. Then over on this side, water only has 1 oxygen in it, so we need 2 water molecules. So the question you're asking is exactly what we're going to do later in chapter 3 and apply
Oh,
and apply it in chapter 4. No, it's a good sign. Like it really, like whenever someone asks a question that it's material we haven't quite got to, it shows that they understand what's going on and see a flaw that doesn't make sense in the way you presented it. And it's because you haven't gotten to, to that yet. So don't feel bad or embarrassed or something. It's a sign that you're on point and that you're getting it and seeing that there's there's some piece of information missing. And it's because we haven't got to it yet.
Yeah, because I was like, I swear hydrogen was 1. And then when you just re-explain that, I just kind of realized like it didn't make sense for some reason.
So we're going through naming and whatnot, and then I won't put that on a test, this part. And then here, what you're talking about is balancing chemical equations. So like this one, for example, is pretty similar. This CH4 is natural gas or methane, same name. And when you burn it with oxygen, you get carbon dioxide and water. So the carbon burns and comes off as CO2. So you need enough oxygens to make the CO2, but you also have oxygen in the water. And we've got 4 hydrogens. So we're going to need more oxygen, right? And you multiply the coefficient is what it's called in front times the subscript behind, right? So on each side, we have 1 carbon, 4 hydrogens, and 4 oxygens. Right, on the left side, what's called the reactant side, it's 2 times 2 gives us the 4. And over here on the product side, it's an understood 1 times this 2, that gives us this 2. And then now a 2 in front times the understood 1 there. So 2 plus 2 is 4. So you're correct. It's just we haven't gotten to laying out the chemical equations and putting in these coefficients to do what's called balancing.
Oh, all right then. Awesome.
Well, yeah, like I said, it's a good sign when someone asks a question that is the next thing we're covering or soon covering.
Good to know. Have a good one.
All right, cool. See you next Monday.